So chapter 2 goes over the first order differential equations, and we're going to attack those with many, well, not many, but a few different techniques. So our first order differential equation means the highest derivative we have is just the first derivative. And so the variables that we'll be dealing with in our ordinary differential equations would be just y prime, y, and the independent variable x. And so I forgot what this was called, the standard form or something like that, is when the highest derivative of the variable is solved for on one side, and then the right-hand side, the other side, would just be a combination of the independent and dependent variables. And since the highest derivative is just prime, then we just have y prime on the left side. Okay? So we have an expression where you have y prime is equal to something with an x and a y in it. And if you remember back in calculus, y prime is the slope of a tangent line. So what we could do is we can set that over to one side, and then we have an expression for the slope of the tangent line at any point x that we have or that we want. And then that slope would be a function of the independent variable x, but also the dependent variable y. So if we have a differential equation, a first order differential equation that we can write as y prime is equal to something, then we should be able to draw a bunch of slopes. It's kind of a weird way of looking at it, but we're just going to look at a bunch of slopes. So let's take a look at our very simple differential equation that we've already seen and know of. And we can use a random variable, random parameter k. Oh, is that locked? You could lock it. It's all right. It's 5 after, right? Sorry. So let's pick a number like maybe 2 or maybe 1, 2. Let's put 2. So this is our very first differential equation that we saw last time. And I don't know if you know the solutions to this, but let's see if we could draw the slope field without knowing the solution to the differential equation. So the slope field says that you want to find the slope given your x and your y value And so what you're saying is that you're randomly going to pick an x value and randomly going to pick a y value. And really, I don't know, maybe I should change the way this looks like and just say I can randomly pick a point, x, y, and then I'm going to find out what my slope is equal to. So, well, 0, 0, maybe. 20, 20. Yeah, it's too big. 1, 1. This is what? 2. 2, 3, 6. How about 4, 1, 2? This can get tedious really quickly, right? So let's just take these sample points and imagine how the graph is going to look like. Okay, it looks like we're just all in a positive in the first quadrant. So let's just focus on the first quadrant, and let's So the way we're going to graph this is not a traditional way to graph things. We're going to graph it by looking at the point that we have. And so we're going to, let's say 0, 0, we're at this point. And then the slope is 0. So what we're going to do is instead of graphing 0 or something weird like that, we're just going to draw a line that could kind of represent a slope of 0. So I think a slope of 0 is a horizontal line. So I'll draw a whole little horizontal line at 0, 0. At 1, 1, we're at this point 1, 1. And now I want to draw kind of a line that represents a slope of 2. So slope of 1 is your diagonal. Slope of 2 is a little bit steeper. And then 2, 3 up here. And that's steeper still. I don't know. That's not vertical, but it's pretty steep. 4, 1. 1, 2, 3, 4, 1 has a slope of 2. That has the same slope as the other one. So imagine that's hard to imagine. Filling those out and then getting some values. Well, again, this whole process is pretty tedious to do by hand. So I would encourage you to check out some links to draw out the slope fields. So our slope field example was 2 times x or 2 times y. So if we were to have a machine do it, well, I let a machine do it, and then this is what we would get. So this is an example of a slope field. So at every point, you would have a line that represents a slope of a solution. Okay? Does that idea make sense? You got the general feel for how to graph it, right? I just did some simple examples and was not interested in plotting more than what we plotted, but that's a general idea. You get a table like this, and then at each point you'll have a specific direction that your graph would be going. So clearly, forgot what I was going to say. Clearly something. Uh-oh, too big. All right. So this is our slope field, which means whatever our solution might be, these would be like tangent lines. But if we're talking about solutions, I can't, what kind of graph am I supposed to draw out of this thing? That's kind of a weird way to look at things. Let's think back to our last lecture where we talked about IVPs. What's an IVP? Initial value problem, right? So initial value problem has a differential equation and a initial condition is what we called it. Same thing, initial value, initial condition. So we have an initial condition. So let's say this is my example, y prime is equal to 2 times y. That's my differential equation. Can you come up and make up an initial condition for me? Give me an initial condition. What would an initial condition look like? Y of what? Y of 1 equals 2. Y of 1 equals 2. So the thing about a differential equation is that when you solve for differential equations, you're just going to get a general solution. And then unless you're given an initial condition, then your solution is just going to be a general solution, which means, what's a general solution mean? You get what? Say it again. It always works. Well, mm, so. Yeah. You'll have unknown constants. And what does that mean in terms of the graph or in terms of curves? What do they call that when you have an unknown constant and you have you could say that you have a family of curves or a one parameter family of curves, right? Remember those phrases? Say it again. Implicit solution is different. Implicit solution means that your solution might not have a graph that looks like a function. And so we'll run into that case also. But when we're talking about an initial condition, you're guaranteed, remember, you're guaranteed that you will find a solution at some interval and the solution will be unique. So you're guaranteed those two things. Now, if you don't have an initial condition, then you just have a general solution for your differential equation, which means you'll have a family of curves. And so all these slopes here represent the slopes for different families of curves, right? So these slopes are for different curves. So remember that you get a family of curves. For a general solution. Now, if we take your example, I don't know what, I forgot what you guys said, y of 1 is equal to an initial condition such as y of 1 is equal to 2. I forgot what it was. We don't have 2 here. Can we just say 1/2? So when we say that we have an initial condition, then we're guaranteed existence and uniqueness. You're guaranteed that you'll find a solution and your solution will be unique. So out of this big family of curves that we have, what we could do is we can go to the point 1. Well, 1 isn't even here. 0.9, 2. So let's say 1 is over here, 0.5 is over here. Did I get that? Somewhere over there. So this is the point 1, 1/2. And from 1, 1/2, right? Your x is, wait, did I get that backwards? No, that's right. This is your x and this is your y value. We'll call it our initial values, x naught, y naught. So from here, what you would do is only from this point, you would follow the curves to see if you can draw out your solution. So your curve has to pass through this point. And then as it passes through that point, then you're identifying your one unique solution of a function. And we could probably try to find out exactly what this is, but for now, let's just take a look at the graph. And speaking of taking a look at the graph, most of these actually allow you to find or input your own solution. So when x is equal to 1 and y is equal to 1/2, you can ask it to draw the solution for you, and then it would draw it starting from that point. Okay? And in fact, you can change your initial conditions, and then you'll have a different solution for that problem. Does that make sense? So that's a slope field. Any questions about slope fields? All right, good. These are all experts at slope fields. No. We need another example. Ali brought up the implicit solution. So this is an example of an implicit solution slope field. So again, we can start off by making sure that your differential equation is written in standard form, where the dy dx is by itself, and so I'd have to divide out by y, I think. X over y. Yeah. So now this is my differential equation, and if I were pretending to do this by hand, I would plot some points just to see how this thing might look like. So 0, 0, oops, 0, 0 is no good. We can't have y equal to 0. We have 1, 0. What's 1, 0 going to be? -1? Wait, 0. Wait, that won't work either. I just said you can't have zeros in the y. 0, 1. Will that work? Yeah, so this is 0. So this has a slope of 0. Let's try 1, 0. Oh, wait. Wait, 1, 0 is infinity. 1, 1. Yeah, that's better. What's 1, 1? -1. All right, I'm done. Let's just use the computer. So there's several of these computer programs, and I don't know which one I clicked on. Let me click on the GeoGebra one. Oops, it's been moved. We still have it. Okay, we still have so this is a different slope field plotter. This has it looks like I can change the x. I don't know. I probably could have changed the x-min, the window from the last one also. What was it again? X over y or y over x? Negative x divided by y. Let's try this window, and let's not do a solution yet. Oh, there it goes. Look at that. Right? So I had issues when I put in y is equal to 0. Look at all the stuff where y is equal to 0. I have that vertical slope. And then at 1, 1 over here, we got a slope of -1. That looks like it fits our model, and then we can check out the rest of them, right? So if we get a solution, let's have a solution. Can I just... Solution A. What? There's some weird things happening here. So remember, the solutions that you want to try to get are y is equal to solutions. and y is equal to is essentially an implicit solution or is an explicit solution. But here, there's weird things that happen. So if I take a look at these solutions for random points down here, I get these weird things. But if I go up on top, then I get these other weird things. So I think what's happening here is that my solutions have to be restricted to a specific domain, and then outside of that domain, some weird things are happening. Yeah. So if you want the full solution to this, it might end up being a circle that we're not seeing because our computer program is asking us to try to find an explicit solution, whereas the solutions that come out of here look like they would be implicit solutions. Okay, so let's say by the end of today, we should be able to solve for these differential equations, or especially this one, this particular one, and then we'll see how it relates to a circle. All right, so let's take a snapshot of this. By the way, have you guys been looking at the notes online? I mean, I don't know if you need to. Are you guys all taking notes in class, by the way? No. You want to see my notes? I think what I'm going to try one of these days, I'm going to try to have you guys not take notes one day. Just listen. Pay attention. That'd be weird, huh? Don't write anything down. Maybe I'll even have you guys stand up and pay attention to lecture that way. All right. So that's the first part of the first section in chapter 2, slope fields. The next part is also trying to visualize this, and we're going to define what's called an autonomous differential equation. And these would fit for a first order differential equation. An autonomous differential equation is a differential equation that does not have an independent variable in the equation. So we have dy dx is our y prime, and then we have some function of y on the other side. Okay? And just as two quick examples, our first example that we did was y prime is equal to 2y. Is this an autonomous differential equation? Our second example that we did was y prime is equal to negative x over y. Is this an autonomous differential equation? No, because there's an x in there, so not autonomous. Maybe I should put that in red. So I don't know if you noticed something interesting from our first example, the autonomous differential equation. But what they're saying is that the dy dx is dependent only on x, which means it doesn't matter what y is equal to. And we've seen functions like that where it doesn't matter what x is equal to, y is always equal to something. That's a constant function. But if you take a look at the slope field for an autonomous differential equation, what we're saying is that it doesn't matter what x is equal to. The only thing that matters is y. Now, if you look, pick a y, any y, and then look along that y, horizontal strip of y that you picked. What do you notice about the slopes? It's all the same. So if I pick a y, any y, and I follow through, and I take a look at all the slopes there, it's all the same slope, right? So that's an autonomous differential equation. It doesn't matter what your x value is, your slope is always going to be the same for that level of y. So that's the nice thing about an autonomous differential equation, is that you're only concerned about the slope. And so if you're only concerned about the slope, wouldn't it just make sense to just describe your whole slope field by looking at one strip? Because this strip is the same as this strip, right? If I look at those two strips, it's like collapsing this into a single graph. So we'll do that a little bit later, but for now, let's take a look at these things called equilibrium points. Equilibrium points are when the slope is equal to 0. So this is saying that f of y is equal to 0, so these are all the y values where it's equal to 0, but if f of y is equal to 0, that means dy dx is equal to 0, so the slope is equal to 0. So equilibrium points are where the slopes are all equal to 0. All right, so what are we going to do with that idea? Where are my notes? There it goes. So if C is an equilibrium point, then y equals C is a constant solution to the differential equation. Such a solution is called an equilibrium solution. I'm going to go back to our example over here again. Do we have an equilibrium point? Where? It's 0, right? So the differential equation was y prime is equal to 2 times y, and that's equal to 0 when y is equal to 0. And when y is equal to 0, we see that all the slopes are in fact equal to 0. So that's an equilibrium solution. Oh, as a matter of fact, it is an asymptote. Yeah. So those equilibrium solutions turn out to be asymptotes for our the solution functions. We'll take a look at that in a minute. If C1 and C2 are critical points and no other critical points in between, then the solution between them then any solution between these critical points will remain between these critical points. In other words, you're not going to have any solutions that would jump up higher than the critical point and come back down. So you're always going to be between, your graphs are always going to be between them. Solutions must be strictly increasing or decreasing. So your solutions, because they're flowing, and then you have equilibrium points where Philip said it was asymptotes, and your graphs are going to go either going up to the asymptote or going down to the asymptote. But it should never touch it. It should never pass it. And never passing it is like the second bullet point that they're saying. So always increasing or decreasing, never passes through those equilibrium points. And then critical points are asymptotes for all these things, all the possible solutions that you have. Okay? So what kind of graph should we expect? Let's say we have, let me randomly draw one. Oh, let me just randomly draw one here. Y times 1 minus y. So these are examples of equilibrium. This is an example. Where's my function? Or my differential equation is y times 1 minus y. So that's an example of an autonomous differential equation, right? And if you solve for y times 1 minus y equal to 0, you're going to get y is equal to 0 and y is equal to 1. And if you look at y is equal to 0 and y is equal to 1, let me see. There it goes. So y is equal to 0 and y is equal to 1, you'll see that the slopes of those at those points are 0, right? 0 slope. Can you see? Where's my pointer? I used to have a pointer here. Oh, there it goes. Yeah, that's it. What? So 0 slopes and 0 slopes. Was that what I wanted to point at? I forgot. Okay. All right. So we see an example of one function over there. Let's see. Let's throw another solution. Here's another solution, right? If I stay between the two critical points, 0 and 1, then my graph is always going to be between 0 and 1. So if I stay above 1, then my graph is always going to be above 1. And then if I throw another one out there, that's down here. So I have three possible solutions for this differential equation, and those three possible solutions follow the rules that we were just talking about. So if we stay within a particular differential equation, or between two critical values in your y, then your graph is always going to be there. But if you look at this from left to right, each of these graphs are either strictly increasing or strictly decreasing. None of them goes back up and has that zero slope business, right? They stay within their compartments. I don't know. Compartments wasn't the right word. Anyways, they stay where they belong. I feel like I should take a snapshot of this for our notes. So they do have special names. These things that we're calling, what do we call them again? Equilibrium points. We do have special names for them, depending on what they do. So looking at the particular equilibrium point, if solution curves asymptotically approach the critical point, it's called an attractor. If the solution curve asymptotically move away from the critical point, it's called a repeller. And if solution curves on one side move away and the other side move towards it, then it's called semi-stable. Y is equal to 1 is a what? Left to right, what's happening to the curves above and below it? They're approaching it, right? So what is it? It's a stable equilibrium. It's an attractor. You see how Y is an attractor? Left to right. Left to right, what can you say about Y is equal to 0? They're repelling, they're going away, so that's an unstable equilibrium. Does that make sense? Is that what? Oh, I don't think so. I think it's a little bit different. All right. So the idea is that you're following these curves from left to right. And then the curves are either increasing or decreasing, right? They're not going to change direction. So the curve is always going to be increasing or always going to be decreasing. And then we should be able to tell whether they're attractors or repellers, whether they're stable equilibrium or unstable equilibrium. And we don't have, this isn't an example, but if we had another equilibrium where one of them goes away and the other one goes towards it, then it would be a semi-stable equilibrium. Okay? So let's take a look at this picture again. So remember that this picture, really, it doesn't matter. In this picture, it really doesn't matter what's happening in the X. I'm kind of tempted to just squeeze this picture. Let's see. Squeeze it down. Whoa. What do we have here? We have the y-axis, essentially. We have y is equal to 1 and y is equal to 0. And then we have the direction of the graph that we can describe. From the top, it looks like the graphs will be going down. From between 0 and 1, it looks like the graph will be increasing. And from the bottom, it looks like it'll be decreasing. So what we could do is we can compress this graph into one axis and describe what this graph is doing and describe all the possible solutions that you're going to get. That is called a phase portrait. So a one-dimensional phase portrait describes the stable and unstable equilibrium using just a one-dimensional graph. And then you can even label these graphs appropriately, where if you see the arrows that are going towards it, that must be a stable equilibrium. And if you see the graphs going away from it, then this is unstable. Attractor or repeller might make a little bit more sense when you see these arrows going towards it or going away from it. But you can say stable and unstable, because if it's neither stable nor unstable, then it's semi-stable, and then that's how you would want to label that. Okay? Pretty cool, huh? Well, remember that our solutions can't ever look like this, because if it reaches the top, then it can't go back down, right? But when you say parabola, maybe you might mean y prime is equal to 1 minus y quantity squared or something. So that might be an example of something that's semi-stable. But you can check it out. Any questions? All right. Okay, so I think we're ready to move into the next section and dive into solving these differential equations. And so this is going to be our first technique, I think maybe our easiest technique. Separable. So the first order differential equations, separable differential equations are probably one of the easier types of differential equations. If we ever run into them, we will be running into them. And the idea is to separate them and then solve for them. So let's take a look at some of the examples that we've already seen and see how we can solve for these differential equations. by separating, you want to make sure that they're, being multiplied or divided, and then you can separate them. If they're being added or subtracted, can't do that. So I think our first example is y prime is equal to 2y. That's clearly separable. Well, what does it mean to be separable, and how do you deal with that? Yeah, so the idea is that you want to write it in Leibniz notation and kind of abuse Leibniz notation by separating the dy and the dx. And so if I divide by a y and multiply by dx, I have dy over y is equal to 2 dx, right? And so at this point, you've successfully separated your x and y variables, your independent and dependent variables, and now you're going to integrate. So this is a step where we integrate, and we're going to get ln of y is equal to 2x. Now there's a plus c on the left-hand side, but there's also a plus c on the right-hand side, so we can just move the plus c on one side and just consider them as 1 plus c that we're dealing with. Now we have some restrictions with the y, but let's for now kind of ignore this and then keep going. This is an implicit solution, but I can solve for this explicitly by using the exponential function or whatever. So this would be y is equal to e to the 2x plus c. Now, some rules for exponents allow us to take our sum in the power and have it as a product in the basis. But then e to the c is just another number again. So we can call that y sub 0. And then we have our general solution for our differential equation. You can call it C. So a lot of people call it A, capital A. But it's just the name. Call it whatever you want. Okay? And then you would be able to solve for either C up here or A down here by using your initial condition. What was our initial condition again? We had an initial condition. All right, so we should be able to solve for this A by using this initial condition. So when x is equal to 1/2, y is equal to 1/2. Wait, when x is equal to 1, when x is equal to 1, y is equal to 1/2. So you put x is equal to 1, y is equal to 1/2, and then solve for this. I get 1/2 equals a e squared, and then a is equal to divide, right? Squared, whatever that number is. So you can just plug that in so that your actual particular solution, is that what we called it? This is a general. Particular solution is going to be y is equal to 1 over 2 e squared times e to the 2x. And you can simplify that if you want. Okay? Any questions? Now, we also had our example. We had another example. Ooh. Was it negative x over y? Something like that. Now this is also separable. So dy dx is equal to negative x over y. Looks like I can bring the y over to the other side. Y dy is equal to negative x dx. And then here at this point we integrate. And then we have y squared is equal to minus x squared. Oh, there's an over 2. Plus c. And then we can bring x squared and y squared over to the one side. And then we can just multiply both sides by c, which we can call another arbitrary constant. In any case, we have a circle, an equation of a circle, right? So the circle is an implicit relation between x and y, but if you need to identify your starting point to be either above the x-axis or below the x-axis, then you would identify either the top half of the circle or the bottom half of the circle. With restrictions, right? Because then beyond that, you're going to have negatives under your square root. Some weird things would happen. So the reason why the computer is doing this is because it's just estimating, and computers are not good with exact values. And so these are all estimates, and then estimates eventually lead to errors. And so this is what happens when it tries to find something that doesn't exist. Okay. If we had an initial value for this problem, then we would be able to solve for that c as well. All right. Any questions? Yes. I guess this is still a general solution. This is still arbitrary. Let's keep it as another constant. So this is still a general solution. Because we still have an arbitrary constant there. Now, if we, like I said, if we're given an initial condition, like we were in the previous one, then we should be able to solve for that arbitrary constant, and then we can settle on which circle we're talking about. And further, you can, decide whether you're talking about the top or the bottom half. Yeah. Yeah. Oh, I just assumed that the graph is going to go down here, and then when it starts going down here with a vertical slope, and then it becomes not a function anymore. Yeah, I'm just looking at the graph. It was semi-arbitrary, but there was some purpose to that. I didn't mark it like it for. All right, any questions? So you guys are also experts at separable differential equations. Okay, now, Philip was asking about some group stuff. You guys have the app in your phone, the Canvas app? Oh, is everybody here? Monica never came. Sorry. Bowen, is that you? What? It's late. Okay. Groups. Oh, here, groups. So I wanted to put you in groups. We have we have 20 minutes. I remember I let you guys out early the first day. So what I want you to do is find the people in your group and sit on, if you have a laptop, you can take it out. Otherwise, maybe you can sit on a computer. So Ding, Mark, and Jay, you guys are group 1. Remember your group numbers. Rami, Hong, and La, group 2. Group 3, can you guys see? Jake, Josue here. Yeah, Josue's here. And Abtin. Abtin's here too, right? Yeah. Yasmin, Abiral's not here. Is he? So I'm gonna have to shift somebody. Randall's here. Carlos, Wonsik, and Zen. Group 6, Shobang, Phil, and Bowen. Group 7, Georgina, Ali, and Jose. Group 8, Raphael, Wing, and Edgar. Group 9, Mario, Brandon, and Travis. Is Travis here? Travis is here, yeah. And group 10, I'm going to take one of you. Oh, Monica's not here either. All right, I'm going to randomly pick Matthew to move groups. Matthew, you're in group 4 with Yasmin. Jake, those guys. All right. Okay. If you are an odd number group, then you're going to do the odd problems on this worksheet. If you're an even number group, you're going to do the even numbers on this worksheet. Okay? All right. Each group is responsible for submitting your work, but only one of you needs to submit it. Okay? It's due on the 28th. All right, there's more. This is due on the 28th. After the 28th, you will be assigned to review 4 of your classmates' work, 4 of the other group's work, and give them a grade. Okay? So let's take a look at the worksheet. The worksheet has links, and you can decide which one is your favorite grapher. But these are the links to the slope field plotters. And remember, if you're an odd number group, you're doing 1, 3, 5, and 7. If you're an even number group, you're doing 2, 4, 6, and 8. Okay? The first 2 problems that you will do will be to draw a slope field, and then on that slope field, trace out, preferably using the computer, trace out a couple of solutions based on the 2 different initial conditions. So the two different initial conditions will yield two different solution curves. And then the second part is going to ask you to take a look at an autonomous differential equation, and either by hand or some drawing program, you're going to draw a one-dimensional phase portrait identifying your equilibrium and identifying them as stable, semi-stable, or unstable. And then you're also going to draw a slope field for these autonomous differential equations showing the different regions. Okay, so if you have two equilibrium points, then you have three different graphs to draw. If you only have one equilibrium point, then you have two different graphs to draw. Okay. All right, you're not going to finish this in 15 minutes. I mean, if you do, then that's great. So I expect you to find a way to contact your friends. These are now your friends, at least for this week. And then find a way to work together so that you can submit your assignment before the due date. Well, I want you to copy the picture onto a document and then save your document as a PDF. Yeah. No. Yeah, just taking pictures of things. All right, so if you guys want to do Google Docs so that you can share documents, or if you want to entrust somebody to be responsible enough to submit this on time. We will have class before this is due. We will have class on Tuesday. This is Tuesday at 11:59 p.m. So you'll have another chance to see each other if you don't see each other before that. I encourage you to take a look at the 4 different graph versions and see which one looks nicer to you. To see which one even works for your computer. You should just have a group text. You guys know how to take screenshots? PCs are the snipping tool. You have a Mac, Control, Control Shift 4. You have to make sure you submit a PDF. It'll only take PDFs.
That's not bad. That's not bad. Yeah, you just gotta save it as a PDF. Simple like W as 1, 2, so the W as 1. another way you can do it, or you can do another different one. For this, we do have to just
By the way, I didn't really lecture much on 1.3. So if you feel like you're getting stuck with the homework problems in section 1.3, in our notes section, there's a video of a little lesson about 1.3 there. That might be helpful.